Have you ever wondered how, in quantum mechanics, particles like electrons or photons seem to behave both like waves and particles? Well, here's the interesting part. Before we measure them, they don't actually have definite properties like position or spin. Instead, we describe them using something called a wave function, written as psi, x, t. This wave function doesn't tell us exactly where the particle is. Instead, it tells us the probability of finding the particle in different positions or states. It's like a cloud of possibilities. The particle could be here, or there, or even in several places at once. Now, before we make a measurement, this wave function can be in what's called a superposition, meaning it's a combination of several possible states at the same time. For example, imagine an electron spin. We can write it like this: psi equals alpha plus beta. Here means the spin is up, and means the spin is down. The numbers alpha and beta, we call them complex numbers, tell us the probability of each possibility. If you take the square of their magnitudes, alpha squared and beta squared, you get the chances of finding the electron spin up or spin down when you measure it. So what happens when we actually measure it? Let's say we measure the electron spin. The moment we do, something dramatic happens: the wave function collapses. That means the cloud of possibilities disappears, and the electron instantly chooses one definite state. If we get spin up, the wave function becomes just. Now the electron is definitely spin up, and if we measure it again right away, we'll get the same result. This collapse is sudden and unpredictable. We can't say which result we'll get before we measure, only the probability of each outcome. That's one of the biggest differences between quantum mechanics and classical physics. In classical physics, everything evolves smoothly and predictably. But in quantum mechanics, measurement introduces an element of randomness. Let's look at another example: position. Suppose a particle's wave function is spread out over a wide area. It's like a blurry cloud of probability. When we measure where the particle is, we might find it at one specific point, say x0. At that moment, the wave function collapses to a sharp spike at that position. Now we know exactly where the particle is. After that, over time, the wave function begins to spread out again according to the Schrödinger equation. But what does this collapse really mean? Well, physicists have different interpretations, and this is where things get philosophical. Copenhagen interpretation. This is the traditional view. It says the wave function really collapses when we make a measurement, and it's that act of measurement that chooses the outcome. Bohmian mechanics, or the pilot wave theory. Here, particles always have definite positions and paths, guided by the wave function. What looks like collapse is just a change in what we know about the system. Relational interpretation. This one says collapse isn't absolute. It depends on who's observing. What's real depends on the relationship between systems. Many worlds interpretation. This is the wild one. It says the wave function never collapses at all. Instead, all possible outcomes actually happen, but in separate, parallel universes. So when we measure something, we just find ourselves in the branch where that specific outcome occurred. So, to summarize, quantum mechanics teaches us that before we observe, particles exist in a haze of possibilities described by a wave function. When we measure, that haze suddenly sharpens into one reality, but which one we get is random. And depending on how you interpret it, that randomness could mean collapse, hidden variables, or even multiple universes.